All right. So we are recording. We're gonna keep going through the code. All right. So I was saying, I'm gonna pick up here, right? We were building the architecture with the multi-head attention, right? And we're going to focus on the attention mechanism. All right. So we instantiate 8 heads. Okay. And each one of these heads is going to be basically the logic that I had covered in this Jupyter individually. Just this time around, I'm not printing out the shapes, but you should keep in mind that's the same idea. K, Q, and V. Okay, so that's the attention mechanism. So you can see that here. So of course, instead of using the y equal wx plus b and dealing with all that, you can just use nn.linear, which is the construct that we have available in PyTorch. So we have nn, we have each head. We instantiate 8 of these heads. So if you notice, we have key, query, and value. That's the K, Q, and V that I did before. Each one of those is an NN linear, and just keep in mind the bias is set to false in this example. We also already discussed the torch.trill, so we saw that, and basically we have a dropout also. So now notice this code here is what does the attention calculation, right? So you have X that goes into key and X that goes into query. That's equivalent to X times W plus B, right? In the previous examples. So this produces K and Q, okay? And now notice that in this line here, you do K at Q, where the at sign is basically the same symbol for map mul that I did before. So you perform the matrix multiplication, and that produces this way, which is the attentions matrix, basically. So this matrix way should be your 40 by 40. You can see that here it says B comma T by T. So T is token 40. So that's why I did the other Jupyter, because in the other one I could print out the shapes, but this basically here is equivalent to what we did before, where we performed this map mul operation, and that resulted in a 32 by 40 by 40. Make sense? So that's the exact same thing that's happening in your neural net. And then after that, way, basically just you use a function masked fill, where you apply this mask, okay? The trill mask that we defined here, basically, this trill mask. And then they are set to infinity with zeros. That's literally what I did here in this operation that resulted in a matrix that looked like that, okay? And that mask is going to be applied to the way, then way runs through a softmax operation, and that just means that that goes into that function to produce new outputs. And then way also goes into a final dropout, and that's basically it. So way at this point should be your 32 by 40 by 40, but it has run through those operations. And as I stated before, the softmax will just, eventually produce values where when the values are minus infinity here, they will become 0. Okay, so once that's produced, you take that, the V. So the V is just going to be value. X goes in to produce V. And then way mat mul V produces out, which once again should produce batch T64, which is equivalent to this one over here. So for this example, we took V as 40 by 64. We multiply it times, so it goes into X, and then the attention scores times V produces batch 40 by 64. So we get the tensor back out. Make sense? So remember, KQ, they're n by 32 by 64, get multiplied, becomes n by 40 by 40, and then that n by 40 by 40 times V becomes n by 40 by 64. And then I have, that's one attention, then I need to have 8 attentions that need to be concatenated. So that's going to be, so this output is only one n by 40 by 64, okay? And then this is a head, right? One head. But remember, in the code we have here, we have 8 of them. So each one will get an n by 40 by 64 coming out in a list. And then that list is going to go into torch cat, and torch cat just does the concatenation. And once I have this out here, it'll be n by 40 by 512. That's it. That's the whole transformer. You know, that's why it's called transformers. If you notice, it's a lot of this, a lot of that going on, right? The attention mechanism obviously is really powerful. So it's almost like you use these operations to create an opportunity where you can compare the x to the x, but after several transformations. That's it. I mean, that's literally a GPT. Once this comes out here, the rest is just should be pretty straightforward. We get this here, right? So this is, we're at this stage, n by 40 by 512. So then we send it to a projection here. And what does this projection do? It's NN linear, N embed by N embed. So what does that mean? Just another layer that maps 512 to 512 in this example. Why? I mean, give it more room, I suppose, right? This is the original architecture of the Vaswani 2017 paper, like literally the same thing. And you should know that these architectures actually have not changed, except that they become deeper, bigger, you know, more heads, more layers, but in essence, it's the same operations, astonishingly. Even though it's been almost 8 years, I think, the transformer hasn't changed that much in terms of like the fundamental thing. Just gets deeper, more heads. You can see how you could you do more heads here? Possibly, right? You could, 64 is can it be divided by 2? Yeah, right, it's 32. So then I could create 16 heads, right, of 32. You see that? So you can play with those parameters and extend things a little bit more. Or instead of 512 embedding, do 512 times 4, bigger embedding, just figure out how to break it and so on. Okay, that's what this code gives you. It gives you some flexibility to create bigger networks. Just keep in mind, though, it's going to be more taxing on your GPU. So for instance, you could have more blocks. So n layer could be 20, 30, 40, right? Easily, just by changing one parameter. All right, so let's take it to the end then. So we have so we finished the head. That's it. That's the hardest part. We are here basically at this out or this out. We go into projection. That's an NN linear from 512 to 512. One more neural network layer. We've got out. We got a dropout layer where some connections will be dropped randomly to provide some improvement. And then we get from multi-head, we get an N by 40 by 512 tensor. That's what comes out. So now let's take a look. So multi-head attention. So that means we're here, right? So self.sa is now a tensor of N by 40 by 512. So then you have this feed forward. So if you look, and notice it goes through the residual, right? So N by 40 by 512 plus N by 40 by 512. So the output of this is N by 40 by 512. The original input was also N by 40 by 512. You add them together, you get N by 40 by 512. That goes into the next layer here. Feed forward. Again, same idea with the residual. What is self FFW? Self FFW is feed forward. So we have to find this class. That's this one. Notice I'm using sequential here again. So this is another example of sequential. So I don't have to do that. X goes in, X comes out, use that X to the next one. Instead, I just do them in a sequence. What is this one effectively doing? Basically, I get a tensor N by 40 by 512. And what happens to it? What is 512 times 4? That should be 2048. All right. So then n by 40 by 512 becomes n by 40 by 2048. Then n by 40 by 2048 becomes n by 40 by 512. Why? It's a feed-forward layer that you're providing, and that's how they designed the original architecture. Play with it, maybe add 3 of those, 1. It does have ReLU activations, but you can see effectively that's what happened. So they have 1 feed-forward layer. I think that's in the diagram, actually. Yeah, so the final linear layer, so it's just that of the architecture. So basically, we did the 6, right? And then what comes out of that assay is the input to this one, which is what we just did. Got it? And at this point, the tensor always is n by 40 by 512, n by 40 by 512. So I think if you always keep that in mind, you can understand how the GPT works. So now we are at the end of feed forward, which is this one, right? So we come out here, that's X. So we are out of each block. So this will happen for each block. So we need to go to this one, the original one. So we did the token embeddings. We did the positional embeddings. We did this part. X goes into blocks and it comes out. So we are basically right there. Do you guys see that? Then what does it do? It goes through another layer of normalization. So this is something that neural networks, deep neural networks are really good at, is this idea of normalizing from, they become good by doing these normalizations from one layer to the next. Now, we've got X here, and notice that the final thing is logits. This is literally the prediction. Okay? So now we are ready to predict text. Remember that GPTs give us text, right? So we need to understand what happens here. LM FFW head takes in X, and let's see what happens. So we're going to look at LM FFW head. It's, again, an NN linear from N embedding to vocab size. So N embedding is what? 512. So N by 40 by 512 will get projected to N by 40 by vocab size, which is what? The vocabulary of your neural network. So in our case, we were only doing letters. So I think we only had like 64 or something like that, right? But those would be your IDs. Do you guys understand? And so now this will ultimately predict an ID for every one of those and compare it to the real. And that's the feedback that it uses to update the weights. Do you see that? So let's take a look over here. So N by 40 by 5, this last layer, LLM head, produces basically here the logits. And you can see I've written the tensor now, no longer N by 40 by 512, but now mapped to N by 40 by 65 in this example, for instance. And so now the tensor would start to predict the IDs, logits, okay? And so these logits would be compared with the actual target value. So if you remember, these are basically our logits over here, and these are the targets, and then you just do a cross entropy optimization to compare the real to the predicted. Does that make sense? So the predicted values to the real values, basically. And it's a cross entropy. Yeah, go ahead, Bruce.
Sure. Targets are typically one-hot encoded, right? I mean, if
targets, so the way that it works is that the cross entropy, the predictions are definitely going to be one-hot encoded because it's the shape, but actually the real labels can be not one-hot encoded. The cross entropy function in PyTorch is designed that way to make your life easier.
I mean, you mean the labels or the targets?
The targets would just be the IDs, yeah.
The IDs, which would typically be one.
They're not one-hot. They don't need to be, because think about it. You could take the IDs and one-hot encode them, and that's an extra step. But all people are doing this. So at some point, somebody said, let's remove that step by allowing the targets to just be the IDs, and then we will one-hot encode them in there.
All right. And what about the logits themselves? They need to be normalized. Like a softmax function should be applied to the logits, no? Because
So, okay. I mean, you can try it, yeah. I mean, I don't disagree with you. So LLM FFW, right? So this is just an NN linear. You can put a softmax there if you think.
maybe
This one doesn't have it. Maybe the results will be better if you do, yeah. I see what you're saying. Like you're used to seeing cross entropy in classes and you have a softmax.
Yeah. The sum should be one.
Yeah.
In the logics.
Yeah.
I mean, maybe internally the cross entropy does that.
I don't think it does it internally. No. So that's a thing that would be outside of the network usually. Whenever I see this, softmax is outside of cross entropy. It's a good point. I don't think this one does it, but it's something you can look at. I don't disagree with you. Try it, yeah. Like you can put a softmax right after that logic, and that's fine. But that produces the IDs, right? So you guys see that? So you went from embeddings, and that final thing the embedding gets projected to one. How? A matrix multiplication. Which weights? It'll learn the weights. Do you see how it works? It's just like you almost always say, I want this, I have this tensor, I want this tensor. And by doing a matrix multiplication, you're giving it this room where you're saying, okay, you're going to go from this to this, but figure it out. How? By learning the proper weights, and that's going to be the optimization process. Okay? So then here in my final tensor, all I have to worry about is that my training data would be in kind of this format, right? And this is how I gave the data, if you remember, the IDs and everything. Did I answer your questions, guys? Do you have any other questions? No questions. So yeah, so this is the optimization. We'll see this. This should be available because we still haven't done the loop and all that. That needs to happen, but I'm just trying to give you the transformations, and hopefully you're starting to see why they're called transformers. They're literally tensor in, tensor out through some weight thing. And they can do even very clever things like the attention mechanisms. Okay, so we got our this thing here. We mapped, where is it? Yeah, we mapped it from n embedding to n vocabulary size. Consider that we'll look at tick token in a little bit. Tick token, the GPT-2 or GPT-3 is a vocabulary of 50,000 subwords, okay? So obviously, that's the more realistic thing that GPT-2 at least uses, 50,000 vocabulary, okay? All right, so I've done this part. I've got the logics here, and then that's the output. So I'm going to go to the diagram to finish this up. So I did this final part over here, n by 40 by vocabulary size, okay? And then this n by 40 by vocabulary size needs to be compared to the real values. Input goes in, predict, compare to real, and that's going to be the whole training process. Okay, any questions? That's the whole architecture. So we're going to move on unless you have any questions. And we're almost done with this. All right, so we've covered this part. So now the cross entropy and everything is part of the class, as you can see. And we haven't discussed generate yet. Generate is once the model is trained, it's going to make reference to its own neural network and predict. Okay, so we're going to look at that. All right, so we move from the architecture. So we instantiated the GPT. This model to device is just so that you can add it to the GPU. Then we have the optimizer where we tie the parameters. This is literally all the weights, right? Tied to the parameter and some kind of a learning rate. So now here is the training function, all right? So this is the training process, very similar to other ones. What do? You're gonna iterate max iterations. If you remember at the beginning, we grab a batch of training data. We've already discussed this function. What was it? You go in the book, let's say we're just doing Huck Finn, find some point in it randomly, take 40, slice it out, then that 40, make a copy of it, One is X, one is Y, and just shifted by one. Do you see that? So you shifted by one. So it's like, boom. So the cat is going, like that. Does that make sense? So we covered this in the previous one so that you get your XB and your YB. Okay. Remember that the model is trying to predict the next token, and then you're going to compare it to that in the real. So now notice here, we just give to M is the model, XB and YB. Because we provided a YB here, then this means the targets comes in here. So then this parameter is true, right? So that means it goes in here in this part, and it knows that it should train. When we do generate, we're not going to provide YB. Therefore, it's not going to do training. It's just going to predict. Okay. So this takes the logits, right? Logits is basically this whole prediction here, right? Comes out. Logits over there. And then targets is what we provided, the YB. Targets. So IDX targets, XBYB. Make sense? Input and output. Right? Everyone with me? Okay. All right. So so I provide X and B, same sentence, just shifted by one. That's how it works. I mean, don't ask me. I mean, this is how it works, right? So that's how it works. And so once that's done, you get your logits and your targets, and you just do a cross entropy of the loss. And you guys know you just minimize the loss. And that's what the optimizer does for you. That's PyTorch will take care of that. All the calculus, gradient descent, all that stuff handled by PyTorch. So you don't have to worry about that. All right. And then that's going to be the training process, right? So you got your loss and logits. And then these are the steps that actually will take the results of loss and everything. And that point in time, it'll calculate the update for the weights and then perform the update to the weights, right? That's what these two do. It's like take the computational graph at that point in time, take all the derivatives that it needs to do, update the weights as it should. Weights are updated. So every time that's happening, and this is the heavy lifting, there's a lot of math going on here, right? But we're not going to derive how this works. This is just what PyTorch does for you. At the end of this full process, though, all that architecture that you created, remember, all the weights were random, right? Initially. But once this finishes, hopefully, those are no longer random weights. Those attention things now actually have proper values where it says robbers and bank. Hey, there's an important relationship there. Do you guys see that? And that's the whole intuition of a GPT. And at this point, we are done. The model is trained. You can deploy it to your business or whatever. And now we just use the GPT to do inference. So in summary, a lot of transformations, right? A lot of these projection operations, keeping that n by 40 by 512 moving. You use these matrix multiplications because they are, in fact, the weights in a neural network. That's the thing that's going to get updated during this training. So now when this happens, they get updated. And at the end, you have that whole network with the correct weights, hopefully, and give it inputs. It's going to start predicting text. That's it. That's a GPT. That's ChatGPT, actually, except that ChatGPT comes out, it's not very good. And then you have to do something called reinforcement learning through human feedbacks, which kind of aligns the prompt and the answer to be a little bit more specific. But we're not going to cover that part in this class. I cover that in 5:30, but in this class, we're just, focusing on this part. So the pre-training, basically. All right. So at this point, if I run this, I'm at a point where I can run this. I just don't know how long it'll take, but I'm going to run it. I don't remember. I don't have my GPU. I didn't connect to a GPU here. It might take a while. It's only one book, by the way, The Adventures of Huckleberry Finn. Remember that this would be trained on all the books in the world if you had them. right? So I'm going to go over here. Okay. All right, so I'm going to go. So it's loading the libraries, all the parameters. Okay, and no errors, right? So I'm going to keep going. Talked about all this. This is the architecture. This is a deep neural network for sure. Okay, so now I did kind of go through this part. It should be training, right? So it's going to start training in a sec, hopefully. So I did these. Did that. Okay, so it's in the training. You can see the star there. I have a print, but it's going to print every so many iterations. So in a little bit, we should see. Okay, now this is not obviously a GPU, so it's slower. If you had a GPU, it would be faster, and that's why you want to have a GPU.
And this one is the GPU that is on the.
Say that again.
Does this thing, is it the GPU that is?
If I had a GPU in this computer, it would use it by default. Because I do have a setting where I can select GPU, but I don't have a GPU available in this computer. I did say that, yeah. That's a good point. I did get Scholar for you guys. And I need to create a document or something so that you can log in to Scholar. So you will have one GPU, each of you, but you can only use it for homework because the thing is, it's a queuing system. So basically, if we all tried right now, we would not get enough GPUs for everyone to have one. So it's going to be more like, on a Saturday at 3 a.m., you'll be able to get a GPU to do your homework assignment, which actually brings up the next homework assignment. All right, so what is the next homework assignment? You're going to train this GPT, but you're going to web scrape some data off the internet. And I'm going to give you so the idea is I want you to build a vet GPT. A vet GPT is a veterinary chat GPT type of a thing. You'll basically need to scrape some data from some websites that I will provide. It's perfectly fine if you use libraries. So you can write the scraper from scratch, or you can use libraries. I'm sure there's many, and you will download text data. Instead of Huckleberry Finn, you're going to train it with scrape data from. So one of the things of the course is to cover like social media data and that kind of thing. So I have some websites that I will provide for that assignment. But yeah, I'm leaving the web scraping to you though. Okay. My suggestion, don't clean from scratch, right? Don't write the Python code to go through all the tags and HTML. Find a library that does it for you. You just need the text. And obviously, the more data you give it, the better your model will be. You will need a GPU probably, so you'll deal with all those problems. Okay. Again, at this, it's not going to be very good. So don't expect it to be a veterinarian. If you have pets, it's not going to cure your pets or anything. It's not going to be very good because you would need massive amounts of data. Okay. But the exercise is to go to pre-train a GPT model using internet data, web data.
Are you going to get the training how to use the GPU or?
Yeah, so the GPU, I'll provide that for you guys next week. I'll look for online. I'll start to create like a link or something, how to get access to. I know I've been told that you already have access to Scholar. So if you want to try it on your own, go ahead, find a GPU Scholar. It's called, Purdue Scholar, and then log in. Your login should work already. But I will describe how to do it. Okay? Does that make sense? So for now, I'll create a link or something, start scraping the data, etc. Yeah, good question. Yeah, please.
Is the GPU architecture that you showed, is this a decoder only?
This is only a decoder GPT. There's only decoder GPTs, in fact.
Okay. So
GPTs
basically-
are decoders.
Okay, so basically the diagram that you showed, this GPT is just the right side.
The right side, yeah,
Yes.
yeah, exactly. So that's a good question, right? So let's elaborate a little bit on that, since that maybe it makes more sense now, right? So in 2017, Vaswani et al. Created this paper called Attention is All You Need. They did it for language translation, and they invented this thing called a transformer. You hopefully the word transformer now makes a lot of sense to you. It's just projections from one layer to the next, right? In a matrix multiplication neural network kind of way, so that the weights can be learned through training. You saw that cross entropy is the loss function, just like MNIST, right? So, but the idea is, the English sentence went through here, it got transformed. Everything that I described for this is the same on this side, like everything, right? So you just account for more inputs, but it's the same thing. So English goes here, it gets encoded, and then you get n by 40 by 512, but it's a totally encoded thing. And then that input, here you would get like Portuguese, I think it was, wherever you are in the sentence in Portuguese. And that's the same, it goes through here, but you would also get the encoded part, and then finally you translate Portuguese. Do you see that? So that was in 2017 by them for language translation. It wasn't even very good, to be honest, like slight incremental thing. Somehow Google then decided to like split this up, so that, like experiment and just say, let's just look at this part or this part. So encoder, when you only use the encoder part of the transformer, this is called a BERT, all right? A BERT model, generally speaking, right? And when you use only the decoder part, this is called a GPT. So what we discussed today is just using GPT and totally ignoring the encoder part. At some point, I will cover this part also. I do have it in my notes. You can start reading through it. It's this, like the BERT models. You can take a look at that, and we'll talk about it as well. Okay, but yeah, just GPT part. Okay. Any other questions, guys? All right, so we made a little bit of a break there to talk about the homework. So as I said, you'll need to scrape some data, replace your Huck Finn book with this data. You really only want text. Really, you would want as much text, like if this was a competition, right? And I said, only one person will get an A. Whoever gets a vet GPT, that's the best. What would you have to do? You'd have to scrape a lot of vet-related data, right? And use the GPU that I provide and just train for many, 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 many days. Do you see that? And whoever did the most of that probably would win. Why? Because there's this thing called the scaling loss. That's actually like the theory of this that says more compute, bigger architecture, more data, better model. That's where we are today, right? And so that's kind of what you would do. So that will be your assignment. All right, so this thing, as you can see, it's still taking a long time. So we'll probably run this again next week. I'll try to have the Scholar GPU and just run it there so that you can see that it starts to train, but it's taking a while, okay? So let's just, we're still not done though. We still have to see how to do predictions with this model, right? So let's think a little bit about that. We have to talk about the generate function, okay? So we're going to look at that part. So that generate function is the thing that starts to introduce this idea of generative models. So I will cover a few other things in generative models, such as latent diffusion and GANs, basically, right? So all these are generative models. All they are is you use the model to kind of predict the next thing, right? So, or predict an image. So now I'm gonna like kill this because it's taking me forever. Okay, and I think even though this one doesn't have anything, my GitHub did have outputs. Yes. Oh, here. No, sorry. Where is it? Okay, go here. Yeah, so this is my Jupyter notebook that I loaded. So this one, Right, so here we are. So the thing that it was running very slowly on the CPU. If I had a GPU, this is what you can expect to happen. One thing I have noticed about GPTs that I really, really like is that the loss always goes down. In other models, you get this instability where it goes up, goes down. I've done a lot of things with this. I always see this goes down. There's something like makes me very happy about that. All right, anyway, so this would be the training, and we would get this. At this point, our model is trained, basically, right? Our model is trained. So now we need to start generating. So we need to give the model something. Now, you guys have probably heard about ChatGPT and you played with it, and they tell you got to become really good at prompts, right? You got to prompt it like this, and then there's a book on how to prompt, and that's really important, right? Knowing how to prompt. But giving these prompts is just basically giving it what? A tensor of the input, right? So that's what you're going to do. So in my example here, I have a prompt, where is Huck? Right? Where is Huck? So we're going to just, look at this to see how that tensor is created and then how that is given to the GPT. And from there, the GPT is going to try to speak back to you, and continue the sequence. Does that make sense? All right. So once the model is trained, we can go over here and you can see the model is called M. So then we would do m.generate, and m.generate is going to take what? SOS context. What is SOS context? If you look at it, it's a torch tensor of some kind. Okay, in this case, I just, I'm giving it like some input, and start generating from there. But in theory, if I give it more, it should give me something more relevant to that sequence, right? So hopefully if I told it, where is Huck, it would tell me Huck is on a raft in a river or something like that, right? So that's kind of the idea. So if you notice, these GPTs are actually already kind of designed for question and answering, or give it an instruction and continue giving you some output. So here, I'm gonna need to create a tensor, which can be just one token, such as in this case, the starting token ID SOS 0. Why 0? Because I'm creating a tensor of zeros of size 1 by 1, where 1 is like the batch size, because my model works with batches. So I'm just giving it 1 by 1. And the value in there is 0, which is the equivalent of the token ID 0. And so whatever that letter is in the encoder, that's the starting point, and it's just going to start creating from there. But that's not all we can give it. We can give it, longer sequences, such as a question. Notice that you do have to do some things like telling it that this is a torch long, like an integer. You tie it to the device, otherwise it's going to error out because the model is tied to whatever device you're using. And then here we invoke mgenerate. Notice I give it SOS context, and notice I give it max tokens, which basically means how much text I want it to generate in like a for loop, right? So that's the thing that we're going to look at, this generate function. And then these parts here are just to extract the data that you get. And then the generated text, notice over here, goes into decode. Why does it go into decode? Because the GPT is producing integers, right? And those integers through the decoder, like that dictionary thing that we created, need to create the actual words or the subwords. Like, remind me before I forget, I want to show you tick token, which is actually a way better decoder than this one. Okay, so that's something that you'll probably need it for your own GPT. Does that make sense? Okay, so I've done that. So now let's take a look at mgenerate, right? And let's keep in mind that it takes in this input SOS token, which is a tensor. So where is mgenerate? So we put mgenerate in the class, right? So our GPT model had init forward. This is very common for most machine learning or deep learning models, but generative models use this like approach of having a generate function in there. So that's this function here. Do you see that? That's generate. All right, so what does it take? It takes the input IDX here and the max number of tokens, right? So IDX is B by T, B is batch size, and T. So I just gave it 1 though. All right, so I didn't want it multiple generations. So then in a for loop, I'm going to repeat the same process and produce a token every time. Okay. All right, so here we're going to crop IDX to the last block size token. So the block size should be 40. So if it exceeds 4, because it only takes 40, right? So if it exceeds 40, you just grab the last 40, right? So that should be the idea. So minus 40 is what? Minus block size is minus 40, right? So it's going to say the last 40 of whatever's in IDX. Okay, you grab that and you give IDX condition, goes into self. Self is forward, so it does the model prediction. Do you guys see that? Any questions? Right, so it's referencing itself, its own forward mechanism, basically.
And what if there's no last 40 words? Is there a bad token or something like that?
If
Like we pick the 12th letter, like 12th index, then there's no previous 40. Like, I mean, is there sort of a padding sequence or repeated start token?
Yeah, I'm thinking, processing here. Let's see. So so crop IDX to the last block size tokens. Block size is 40, right? Let me see here. It's one of the parameters that I think are global variables. Yeah. Block size is 40. So this is an indexing. Think about this. Where are we? Here. So IDX. So IDX is 1 by 1, or it could be 1 by 3, or 1 by 10, whatever you give it. I take it in the first time. So I think I want to say that it takes whatever it is or no more than 40. That's how I would interpret it. Does that make sense? That's the only thing that makes sense here.
Yeah.
Right? Because obviously I can give it 1 by 1, I can give it 1 by 10, but I'm just saying here no more than 40. I mean, we could do it. We could do an experiment, like think of a tensor, index it. How could we do this? Do you guys know what I mean? Like, help me out here. Let's create a tensor, right? Let's go here, actually. It's a good question. At the very beginning, I had a tensor X. So let's create a tensor that is 1 by 4, let's say, right? And I'm going to add a few more here. So I run this one 1 by 4. It's kind of the same. 1 batch, 4 integers. Now I'm going to do that thing of the index, the slicing. So that was in here, I think. Okay, so this is doing this. Let's see what happens. Okay, but I have to do X in this case. X. Oops. All right, so I'm gonna, and block size would be 40. Block size 40. So all rows, which is 1, minus 40. 40. keeps it. Yeah. So, yeah. So nice, handy thing. So it does keep it. So it's basically, if it's greater than 40, it'll cut it out, but otherwise it just allows it to go through, and that's very handy. Yeah. Perfect. Awesome. All right. So let's keep going then. All right. So I go back here. Nope. I'll close this because it's confusing. This one. All right. Perfect. So we take our IDX. We can't allow it to be more than 40 because it's not going to fit. We give it this. It becomes IDX condition. IDX condition goes into self, right? And then basically it's going to use that data to produce the loss and the logits. So that becomes your X here. In the GPT model, right? So it just goes through the whole thing, right? And it's going to produce the output. In logits, basically here, or sorry, loss and logits. And then here, focus on the last one. So the last predicted one, basically, right? That's the last thing that it predicted. This goes into, there's your softmax, actually. That's your softmax that you had mentioned before. The logits comes out. It goes into softmax to produce the probabilities. And then from here, you use torch multinomial to select basically the index of the highest value. And then this IDX gets added. So IDX next and IDX, which was the original one, get concatenated. And now IDX has one more element, basically. Do you guys see that? And then that IDX is in the loop. So it's going to take the IDX again and keep repeating this until it reaches max tokens. And then you've generated all the IDs that you have. Unfortunately, I can't run this in real time because I didn't train the model. But does this make sense, guys? Are there any questions? All right, so you give it the tensor, right? You give it the tensor. You give that input to the model will predict logits. You grab the last one, and then you run it through the softmax, the thing, and then predict the, out of 64, the one that has the highest value. And then that's your, that gets concatenated to IDX. And at the end of the day, you return IDX. Notice that IDX will have the initial thing plus what it predicted, right? So whatever you gave it, let's say you gave it, you know, the 10 indices that you gave it, whereas Hux, it's going to return that back plus what it continues predicting after that. And that's basically the generate function. Any questions? Do you have a question?
Yeah, I mean, in this case, in the generated part, we are sort of generating 39 tokens, which we don't need. And just use the last token and then concatenate that. I mean, that's what we do when we are taking the last logic, no? Focus on the last one.
We are. That's, yeah. So I'd like to print these values. So, well, we did this, and this was 4, wasn't it? So,
yeah, I'm talking about.
And then that goes in the last part. You're saying it generates n by 40 by 512, but we only care about the last one.
The last one, yeah. So, I mean, I'm just saying that
it may be.
It works, but we are sort of needlessly generating 39 tokens. Typically won't need, right?
This would be a nice thing to like run and print out, actually. Yeah, because we could print out what this what these are, right? Like the shapes. I don't have this printed out, so let me see. Yeah, just generate just gives like the text. Trying to. So definitely, so this is definitely out of 40, the last one. intuitively, I would think it's 3, 4, 5, 6, but this part I'm not sure. We'd have to, so here is n by 40 by 5. So here's another thing that's might be throwing me off. So training is done in teacher forcing, which means you do give it the whole centers and shift it. But that's only training. Testing is not teacher forcing. So we have to account for that. So in training, this makes sense. Like this is might be just in reference to training. But in testing, I want to say no, but I'd have to print it. Let me, maybe in the answer should be here, actually. So the answer should be in this thing. So n by 40 by, well, oh, I think I know. So n by 40 by 512 produces n by 40 by 512. But if I put n by 3 by 512, I should get n by 3 by 512, but shifted. So I just grabbed the last one. There's the answer.
Yeah, but still we are generating 2 tokens which are not needed, right? We just grabbed the last one, but we are generating 2 tokens which we
I give it 3. Yeah,
Yes.
the shifted, yes. So the cat is sleeping. So you're saying we ignore these 2 and just grab the last
so
one.
it's so-
Yeah. Yeah. I can see that, but that's right. That's actually right. That's how it works. That's a good catch. Did you guys understand that part? Did that make sense? So, you know, n by 40 by 512. Remember, this is something that can be confusing, right? When we train a GPT, we use teacher forcing, which means we always give it real data, shifted, so that it doesn't generate incorrect things, and then it trains on incorrectly predicted things. Okay, so n by 40 by 512, but really it can be n by 3 by 512. So n by 3 by 512 goes in, where is Huck? Out comes n by 3 by 512, but where is Hawk? Is Hawk River, right? So that's basically how it should work. Got it, guys? Yeah, that's a good one. I wish I had, maybe I'll print that at some point, but yeah, that's how it should work. All right, so then let's go back to generate here. So yeah, we grab, you know, we make sure it doesn't go over 40. We give it the input n by 3 by 512 or whatever, n by 3 by, you know, no, n by 3 actually. Then it produces, and then we grab the last one, and then it goes through softmax. Then we've got the select the highest one, and then that ID gets added to this, and we just keep doing that. Eventually, this would be whatever 500. So it would be n by 500 probably by, yeah, by that. And that would be your output of your model. And then that IDX then over here is what comes out here, but then that goes into the decoder, and boom, we translate into that. That's the text. So I trained this. You see the iterations there from Huckleberry Finn. Not great. Seemed that man come out Silas. He warrant one more, or money by Ching, and so on. But it's not great. Obviously, you know, to get really good results, you know, it takes a lot of work. That's why unfortunately, the state of the art is that only OpenAI and Meta and companies like that can pre-train these models. In 530, which is not, I'm not pitching my class, but I'm just saying in 530, we cover that. So no longer PyTorch from scratch. Instead, you'll download Llama 3 or whatever, GPT-2 with Hugging Face, and then we'll do fine tuning. But I don't cover that in this class. Okay. All right. So yes, sir.
Just drop a question.
Pardon?
Will we get into trouble if we train on this data set?
In which data set?
This data set.
Huck Finn?
Yeah.
For the homework?
Yeah.
Well, the requirement though is that you need to train on the vet data.
Okay.
Yeah. Why would you?
The fourth line.
I didn't see that. Sorry about that, guys. Well, that brings us to the point. Ethics in AI. Okay. So there's a course. Sorry about that. So there's a course in or in all programs, right? That is ethics in AI. And we are training these models on a lot of data on the internet, right? And there's a lot of toxic data on the internet. And unfortunately, people work really hard, not unfortunately, but they work really hard to try to remove the bad language, remove bias. Those are very, very important things. ChatGPT's got safeguards and all that needs to happen. That's an active area of research. But it's difficult to deal with. Okay. And I apologize for that. I didn't see that. All right. Does that make sense? All right. So for your homework assignment, as I said, you will download data from the web. And it'll be, the goal is to create a vet GPT. All right. So now that I did that, comes this example. So I still want to do tick token as a last topic, but let's just wrap this one up. Remember, we're using an encoder that we created a dictionary. Here is Huck, right? So then that would create a list of integers. So basically encode it into new list. New list goes into NP array. And there you go. We have a list of integers. That's what goes into the GPT, right? Make sense? All right. So then once this is a NumPy array, GPTs don't accept NumPy array, so it needs to be a torch tensor. So new NP goes in here, torch lang, device, just make new context into a torch tensor, basically. Okay. And then here, this step is just creating what? Because the data likes batches, we're creating a batch of one. So it becomes a 1 by whatever, however many items are there. Does that make sense? This view thing here, 1 comma minus 1, creating the batch of 1. So that's just a formatting thing. My data is ready now, a list of integers, and that's new context, which will go into generate and tokens. And from there, it'll start generating, and we just grab the last element. Got it? All right. So here, once we generate the text, we're going to do decode, and then where is Huck? And then it starts generating text after that. Notice that this is provided. The input comes out in the tensor, basically. And that's your ChatGPT right there. Minus RLHF and minus $8 million and minus 1,000 or so GPUs and minus all the books and the internet and everything. Okay, but you know how to do it. Yeah, so great. So we finished GPTs. Perfect. Next week, we will move on to a new topic. I still need to think about a little bit what we're going to do there. I'll check the syllabus, but I wanted to definitely cover this topic as this is your next homework assignment, okay? And this homework assignment has to do with the challenge of creating data sets. So, it's nice when you have like the previous homework assignment, I gave you 3 data sets. They were already formatted, they were already CSVs, right? In this homework assignment, I'm not giving you a data set at all, right? Instead, you guys have to collect it and, our syllabus says that it has to be from the web. So we're going to collect some websites, right? And you guys can create. So remember, you're going to use something like this to create a vet GPT. And the idea, we'll ask it questions, how do you treat a dog for this and that? And it'll hopefully give us an answer. Obviously, don't expect it to be very good. That's the whole point. All right. So we completed GPT. So now let's go ahead and look at tick token. All right. So what is tick token? So I did this dictionary here, right? I did that, and that was based on letters. I also, for those of you that are reading the notes, I provided a section in here called data wrangling. So you can read through that data or through that chapter. Yeah, here. So data wrangling from scratch, read through that, and it should give you a lot of insight on how to create your own dictionary, but a more robust one. I think this one was at the word level, okay? Now, obviously, if you were doing this correctly, you'd want to use tick token, which is a library in Python. We may need to install that one. And it's the professional way of dealing and creating this dictionary or using a dictionary. All right, so I'm going to go ahead here. I'm just going to continue with this Jupyter. Okay, so. Okay. Actually, let me create a new Jupyter. Sorry. So we have enough time, I think. So it is spelled tick token. So tick token. So this actually has an underlying algorithm. What does that say? Tick token has an underlying algorithm called the BPE algorithm. Okay, so it's you're basically going to create a tokenizer. I'm going to do import tick token. I don't have it, I'm sure. Yeah. So I'm going to have to install it. Okay, successfully installed. Okay, no errors, right? So we have our library. So this is actually, from my understanding, this is what is professionally used. You don't want to implement the BPE algorithm, most likely. I can give you some insight into what it is. It basically is, so you have, we don't, the vocabulary that we use is not based on words, right? And it's also not based on letters like the example I provided. So in the example I just provided, we had 65 letters, A, B, C, So we don't use that. And we also don't use the word cat because we want to take advantage of the fact that happy, happiest, happier, happily, right? And what about an example like this? iPhone, right? You could, if you communicate with some person and you say to them, I was iPhoning yesterday, you would understand that, right? Like that has some semantic meaning, right? And so GPTs have the capability to understand something like that and to even create something like that because they'll take iPhone and ning is an ending of a lot of words that has meaning, right? So what it does is it'll take like iPhone ing and it can learn things like iPhoning because it has learned walking and training and so on. You guys see that? So that's why we want to use something more similar to syllables. So, but actually we don't use syllables either. in GPTs. Instead, you're going to use something called subwords. That's the technical term, subwords. But it's like a syllable, except that it's a syllable that it's created by an algorithm such as BPE. So the algorithm will look at sequences of letters. Like it'll start with a basic letter and then it'll start putting them together, right? So in English, the letters R, CH don't likely occur, right? So it's going to look at something like that and not see it as useful, right? But TH, the, for, whatever, a whole bunch of words will use TH. And so it might then figure out that that's a worthy subword to have. So it basically calculates those things and it looks at the frequency of occurrence in like a data set. So it assigns IDs based on that. And that's it. So your vocabulary will have IDs from 1 to 50,000, which is what I believe TikToken uses right now, made up of these subwords, which are kind of like syllables, but not really. Ing, for instance, for iPhoning, that ing could be one of the subwords with a specific frequency that gives it the ID. Okay? Does that make sense? That comes, that's basically and beyond that, how the implementation is done with BPE, that's not something I'll cover in the course. You can read up about it. Okay? But that's how it should go. All right, so we've got TikToken. Now let's bring it in, right? So we're going to bring it in for GPT-2. So I'm going to create what is called a tokenizer, right? So I'm going to do a tokenizer, which is going to be TikToken get encoding and then I'm going to say GPT-2. So basically here I should be able to get the encoder for GPT-2. Got it? You might imagine how this might allow you to get Meta Llama and things like that. Okay, so let's run that one. All right, so it took a little bit because it's not necessarily tiny, right? But this is our dictionary. Just like you saw in my code, although it only had 65 letters, it was a two-pass problem, right? First, we created the dictionary. Once it was set, then we did the GPT training and all. So it's a two-part problem. So here, obviously, I don't know how they trained for GPT-2. They probably gave it all the books in the world, whatever, and then ran it through the BPE algorithm, which in the end gave you this vocabulary, okay? So then I'm going to create some text, and I'm going to encode it, basically, using this approach. And what we should get, just like before, is get a sequence of integers because you have learned that integers get mapped to embeddings. Okay, so in this case, I'm going to create a text. And I'm going to say, so let's say, hello, do you like tea? Something like that. Okay. Okay. All right, so let's run this one. Am I missing something? Yeah. Oh, yeah. Sorry. Double quote. Thanks. All right. So I have my text here. Now, tick token. I'm going to create the integers. Remember, that's the thing that I need. Integers. Tokenizer dot encode. Oops. Okay. And I'm going to give it the text. Okay. So now I've generated the integers, so I'm going to print them out basically. And there you go. So instead of creating it, we are taking advantage of this more powerful, better dictionary. So I challenge you in your homework assignment to use this approach instead of the one that I gave you in the example. Do you guys understand? Yeah, everyone with me? So again, this will be a subword type of an operation. So the code will print out, the IDs. And then, of course, we want to convert the token IDs back to text. So in that case, see how we do that. Oh, I have it here. So I did encode, right? Yeah, so we're going to do decode. So this would be what? Strings, tokenizer, dot decode integers. All right, that worked. Strings. Hello, do you like tea? And that's basically like literally what I did with the ABCD from beginning to end. But now you have a slightly more powerful thing to try out for your homework assignment, tick token, which is the professional thing to use. So yeah. Okay. All right. So I mean, it's simple, right? So it's not much. I was gonna say something and I kind of forgot it. We can try other ones. I don't remember what Llama 3 is, unfortunately, but it may not work. Yeah. Could be like Meta Llama or something. So you have to like figure it out. And I only wrote GPT-3. That's you read my mind. So GPT-3.
I think there's not be that GPT 3.5.
3.5. I just don't know how they wrote it, They're not public either. Yeah. Yeah. So GPT-2 may be what we have. I mean, there's a whole bunch of things you can do, I'm sure, to print out. I know for a fact what I wanted to say, there's about 50,000 subwords. Okay. So it's actually not that much. I was surprised. I thought it'd be like hundreds of thousands. And when I looked into it, actually, it's just 50,000. So that was pretty interesting. Oh, I remember now what I want to say. There is no unknown token. That's what I wanted to say. So in my data wrangling thing, I created an unknown token. And because this used to be the practice, you'd have an unknown token for words that you. BPE doesn't need that because it just creates letters. And from there, it can actually create everything. That's how amazing it is that. So definitely BPE is an algorithm that's amazing and contributes highly to the success of GPTs, but just it's outside of the scope of this semester. Okay. All right, guys. So that's basically it as far as me. I just look for the next few days for a link for the homework. I'll provide some examples of where you should scrape your data. I have some vet GPT websites. As I said, get a library to do this. You don't write the code from scratch, but definitely download the text so that we meet that requirement of the social media thing. And then you will take that text and train a GPT. I also need to provide the GPU Scholar thing because as you saw, it won't train fast on a GPU. And then you can use something like tick token. And then that will be your next homework assignment for the next few weeks or so. Got it? Next week, we'll start a new topic. Okay, we'll cover a new topic. I'll check the syllabus. We'll go from there. All right, so we can stop here for today. I'll stay a few minutes if you have questions about anything. I've finished grading your exams and everything, so check on that as well.